Good morning, everyone. Thanks for coming for this very early session. So my name is Ulugbek Kamilov. I'm assistant professor at Washington University in St. Louis, and I work in the computational imaging group. That's my research group there. And basically what we specialize on is developing algorithms for trying to integrate different types of imaging systems together with algorithms. And that will be the topic of my talk today. But the way I want to get started is basically the really topic of my talk will be kind of integrating imaging with machine learning, right? This is something that has captured our imagination in the past few years. And I think many talks here, and this workshop is completely focused on that topic, will be around that topic. But before I get started, let me do a little quiz that I did on my Twitter, and I also did in the class that I teach at WashU, and I always get interesting answers. So who here, there are two answers. So deep learning is, and then raise your hand if you think one or the other. So the first answer is, who thinks deep learning is a massive bubble that will be gone in 2 years? It will completely disappear. Good. So who thinks deep learning is completely, life-changing technology? Everything will be completely different and changing. Good. You see? So this question, actually, the reason I like this question is two extremes. It makes us think about it. And then here's, I asked this on Twitter, and here's the distribution of votes I got. Ignore the fact that I couldn't fit it in, so I divided it up. So you can see people are roughly divided, but majority up to November 2019 was still voting that it's a massive bubble, right? We do feel that in some sense. We do feel like it is a bubble, but many of us are skeptical when I tell it it will be gone within 1 or 2 years, right? Many of us don't think it will be gone within 1 or 2 years. So today I want to talk about basically the way deep learning is affecting computational imaging in particular, which is my area of expertise. And for that I want to take a little step back, right? So if we think about imaging, in the past it was really a kind of a hardware exercise. You would have an object in three-dimensional space. You try to map it on a film or eyepiece, and try to build up the systems that would map this to, right? Now, what happened later, we ended up with nice computers that allowed us to do the digital signal processing. So it suddenly gave us a lot more freedom. We could enhance things, we could denoise things, we could process things a little bit, right? So that's where we are now, but very near future. So here I put future, but it's actually near future. All of us here are contributing to another type of things that we're evolving to imaging, where the information collected through instrument gets combined by information collected from outside the instrument, which gets aggregated in some way to help us extract information which is potentially hidden on this side of the pipeline. So we can potentially extract something more than we collected on this particular instrument, right? How do we do this? Well, there are data sets. We train models, and those models hopefully allow us to do data analysis that we couldn't easily done with traditional non-data adaptive signal processing. And this is the direction I want to go. And in particular, I want to go in the direction by considering imaging inverse problems, which is something people have talked about. Michael have talked. In fact, this image I took from his slides, which he uses, and it's his favorite that he's been using for a while. So I'm going to talk about imaging inverse problems. So how do we think about that? So we have a forward problem, which is basically unknown quantity. We cannot observe this quantity, but we observe some form of realization here, which goes through some deformation noise and some kind of operator age. What we really want to solve is, in fact, the inverse problem, which is recovery of the unknown x given those measurements y, right? So that's really what we're going after. However, and this is very generic formalism, which can be applied to many different settings, and all kinds of imaging systems can be represented as inverse problems, as we know. And then once you formulate it as an inverse problem, now you can speak one language to try to address them by using mechanisms that we have, right? So that's an inverse problem formulation. So what are the challenges? Okay, let me give you a couple of examples. So one example I'm going to talk about today is magnetic resonance imaging, and some people here have worked on it, and we've seen some talks. In magnetic resonance imaging, basically we collect the data in the Fourier space. So here you see a little illustration that as we collect frequencies, so this is K space, which is essentially two-dimensional frequency space, as we collect measurements there, then we can take the inverse Fourier transform and form the image. So the sampling is done in the K space. You can also form 3D images by doing volumetric images by collecting things across several slices. So this is 3D MRI that we do, right? And the second example I want to talk about is optical tomography, optical diffraction tomography. Who is here familiar with optical tomography? So at least few people. So the idea is pretty simple. It's just like traditional tomography. We have some 3D objects that we want to image. And in fact, that object is something specific. For every location inside the 3D volume, we want to know a number. That number is a refractive index. Okay, it's a refractive index. It could be a complex number. And it does two things. If I plot that thing, of course, I can see some structures. But the second thing, if I look at the refractive index, it also is a quantitative metric that tells me something about the object I'm looking at. It's physics about the object, so material properties. And how do we do it? Just like in X-ray, we put some light, but it's going to be coherent illumination, for example, a laser. And then we can model it as a plane wave. It's going to go through the object. On the other side, or in reflection, somewhere we have a sensor, which is going to measure the light field coming out of the object. And of course, the measurements are discrete, digitized. This is like a camera. And in fact, if you look at what you would observe, it might look something like this. So this is a light intensity measurement at the camera outside of the object. Now, there are several problems with this thing. Typically, the light fields are complex. Cameras don't collect it, so we have phase loss. We lose information of the phase. In some cases, you can get it by using holography. Interferometric techniques can get you. But essentially, the goal is, given this form of measurements, to go back and recover the image. So this is for one illumination. Typically, it's not enough. Just like in traditional X-ray tomography, we need to change something. For example, the angle of illumination. We do many, many images of this form. So typically hundreds or thousands for 3D images. And then based on that, we try to recover the refractive index distribution. Okay, so those are the two applications I really want to talk about today. One is magnetic resonance imaging. In fact, 4D MRI, 3D plus time. And I want to talk to you about optical tomography. So what are the typical challenges, right, when we look at inverse problems? So many of us know already, but let me highlight some specific ones. So the first one is slow acquisition. Okay, so why is it slow acquisition? In fact, there are two reasons. We don't collect the data in the image space. Okay, we collect it in some other domain. And the second, we do sequentially, right? So this is in a K-space collection. And in optical tomography, we collect like projections or interferograms of the images. So we have to collect many, many projections to be able to form images. So what's the second problem? Imaging artifacts. So why do we have imaging artifacts? Well, there are some limitations that we have with hardware, with subsampling or model mismatch, which means our interpretation of the data is not correct, the way we're interpreting, and could be actual measurement noise. So here's an example. This is a MRI example. So we have a moving object. We do a 1 minute scan of a 3D body, so it's 3D plus time, and then we try to do inverse Fourier transform. So if we do this, we would end up with this kind of streaking artifacts. So it's a terrible quality. And this is an example from Michael's paper, in fact, with optical tomography. If you do, you can see here, this is a scary example. There are two identical beads, in fact, put inside the medium, and you try to collect it. And if you try to do the imaging by using linear forward model, means you assume the light interaction is linear, you can end up with wrong shapes of the object. So in fact, it should be two identical beads put in, but we get deformed images, which is a little bit scary if you think of imaging giving us something which is not exactly what it's supposed to be. And here we have, I think, those are yeast cells. Again, the same thing. You can see they're completely deformed because of the model.
Deformed, or is one correct?
So you have to actually see the corrected one, which actually I don't have it. Maybe in the paper you can see they should be actually completely symmetrical. So here one became smaller, one became a little larger.
Okay, got it.
Okay, and the reason is twofold. There is a missing angle because of missing wedge problem, because you cannot scan it fully. But the second problem is the model of interaction between the two is linearized, which is not true. So that's why you get this form of shapes. Okay, and finally, high computational memory requirements. So this is a nice example from Frank Ong. So this data, for example, forming this image would take you 100 gigabytes of data to process. So it's pretty large scale to deal with. And this is very common in MRI data sets I work with. So here are the three examples of what we want to address. So now, how we want to address today, I want to talk about one specific family of algorithms I was working last year, which try to combine two things, which try to combine what we know from optimization, but also some elements of machine learning as prior regularization. So really going towards the optimization frameworks, efficient optimization by using priors which come from neural nets. So especially I'll cover those 4 papers as we go along today in the presentation. But the perspective we're going to have is as follows. Our perspective is to formulate inverse problem as an inference problem. So we have two elements here. We'll have a forward model, which I put here as a likelihood function, which describes the physics of data acquisition. So this is a little bit counter-traditional way of thinking about deep learning, right? So we're trying to put some form of specific models, which is not something, traditional deep learning or Jan LeCun style deep learning on Twitter doesn't really promote. But the reason we really want to have forward models, there are several reasons. Because in some applications, we really do need advanced forward models to take into account. For example, if we want to correctly interpret the data, we need to bake in the actual physics to be able to interpret the data. That's the physical models. Or we might have some known error sources that we can actually model that we want to use that source of information without just extracting from the data. So that's a forward model description. And then we want to explicitly separate it from imaging priors, which try to constrain the solution set. And we need advanced priors to combat the things I told, long acquisition times, incomplete measurements, and noisy measurements. So this is a prior, and that's where the data aggregation component comes from, where we have data sets, and we try to get that into a neural network to use in inverse problem. Okay, so I divided the talk into three topics. So the first topic will be just reviewing the proximal optimization. Who is here familiar with proximal optimization or proximal algorithms? So few people. So I'm going to spend some time to go over this, because this will nicely lead into the next two things, which are actually talking about using deep learning within the framework. So the first approach is regularization by artifact removal, and the second we gave a very cute name called Simba, which is essentially kind of trying to do sequential optimization algorithm for large-scale problems, tomographic problems. Okay? Any questions so far? I can take a quick question. Good, so let's start with imaging as inverse problems, okay? And what I want to start with is the most fundamental imaging inverse problem, which is image denoising. It seems very easy, but in fact, in many ways, it's the most complicated one, okay? And I'll explain you in a second. So let's say we have this very simple problem. We have z equals x plus e. X is what we want, e is what we don't want. So there is signal and there is noise, right? And we want to separate that. What's the complication? Well, the problem is, how do we separate one number into two? So there are infinitely many solutions, right? And that really brings us to the core of imaging inverse problems. You might have infinitely many solutions. You're trying to separate things into what we want from what we don't want. So how do we typically solve it? Well, we design this kind of algorithms called image denoisers. So what's image denoiser? It's basically a function, so here I put a d, which takes in a more noisy image, hopefully z, uses some information we have about the problem, and gives us less noisy image. Okay, so maybe as the input you have something like that, as the output you have something like this, right? That's what we really want to have. So what are the examples of image denoisers? So for example, a very popular example was proximal operator. So now that's, for people who never seen this language, might sound strange. But what's proximal operator? It's a special type of denoiser. So if you think of a general denoiser, it goes from more noisy to less noisy. Proximal is a special type of denoisers that can be written as an optimization problem of this form. Okay? So think about it. So we have an operator, which is the same thing. It takes an image z as an input, and it returns some x, which is a less noisy image. Okay? So it's just a function like this, of this form. But it has a specific shape inside. It has two terms. If you ignore the second term, if I set the tau, this constant tau, to 0, the output of this minimization will be z itself, which means we're doing nothing. It's identity. Okay? So this is a z equals to 0. If I start increasing this tau, this minimization problem will take into account this h function more and more. So whatever this h does gets embedded into this image, gets promoted in that image. So as I increase the tau, you can see I'm putting in more and more structure for h. So h is what allows us to put the prior information to separate the signal from noise. Okay? So all I want to remember you at this slide is a proximal operator is some form of image denoiser that can be really written as an optimization problem. And now I'll give you a specific example. So the reason I want to talk about this because proximal operators will be a natural bridge from image denoising to other types of imaging inverse problems. Okay? It's a very fundamental unit that we want to look into. So let's look at a very popular example. So this is also from Michael's slides. It's a wavelet domain soft thresholding. Who knows wavelet soft thresholding here? So more people than proximal optimization. Okay, so what's wavelet thresholding? So we'll have some image here on the right-hand side. You can take a wavelet transform, invert wavelet transform, and it's just a transformation that has the same number of pixels, but you can start throwing away smallest pixels. Okay, if you start throwing away smallest pixels, what you're going to see is that you can throw away up to 90% of all the pixels in the wavelet domain without losing much of the visual quality, which essentially means that images are wavelet compressible, and many people have kind of heard it at different contexts. At some moment it degenerates, but by that time you throw away more than 99%. Okay, so how can we do the denoising algorithm by using a wavelet transform? So here's a simple denoising algorithm you can design. You can design a denoiser that tries to return an image which is close to a noisy image Z, so that penalizes the distance, but minimizes L0 norm of the wavelet transform. So L0 norm basically counts number of non-zeros. Okay, so we try to have a minimum number of non-zeros. Okay, so noise will not have this property because if you have a white noise here, it will also be white noise in the wavelet domain. It will not be sparse. Okay, now it's a non-convex thing, so what people typically do, take the next best thing, they pick L1 norm as a convex problem, and they try to do this denoising. Now if you do this, you can end up with a very simple algorithm, which is called wavelet thresholding. You take to the wavelet transform domain, you pointwise shrink small coefficients because you say those are noise, and you take the inverse wavelet transform. Okay, and this is in fact a proximal operator. Okay, so it's an operator that can be written as this form, and this is the image that I showed you before, in fact, the output of this algorithm. So by controlling this tau, you can start removing more and more wavelet coefficients, which means you're imposing more and more the structure. Okay, so this is an example of proximal optimization. Now, how can we bridge this to more general inverse problems? So let's consider a more general inverse problem, var hx. So now h here has a lot more things than noise. It has some subsampling, some physical information, some model uncertainties, whatever you want can be represented with that h, which could be nonlinear operator or linear operator. Right now we want to solve this thing. So we can formulate it as an inverse problem. So we formulate it as a regularized optimization problem. Now we're going to have two things, data fidelity term and a prior term. So this is basically one way of formulating this problem. So this is a classical example is linear inverse problems where you have a quadratic data fidelity term by assuming Gaussian noise, and you have a quadratic prior, and if you do, you get a closed form solution to this thing. So that's known as a filter back projection. The assumption here is Gaussians. Or you can take a more general perspective where you take a maximum a posteriori probability, where you take negative log of likelihood of this function, and then you take some prior statistical distribution of the prior. So then you end up with a map estimator. Or more popular examples from sparsity area, you could take a quadratic term for data fidelity term, but take sparsity promoting, for example, total variation that Stan Osher and others have developed for non-smooth regularization. Now the key here, this is non-smooth, it's a non-differentiable thing, but it promotes sparsity in the transform domain. Okay, so now we can formulate it as an optimization problem. So now what I wanted to do is, once you think of formulating the general inverse problem as an optimization problem, and you think of image denoising, now we can think about two optimization algorithms which have been extremely popular in the imaging inverse problems. Okay? One is FISTA, one ADMM. Both solve the same exact problem, which is F, G plus H. Both get us the solution of the same type of optimization problems. And both have different structures, but those structures are very interesting if we look at it in detail. So this is what's called FISTA algorithm, and this is ADMM algorithm. So let's look at the structure of these things. So in the FISTA in ADMM, the first step has only G in it. So it's a G term, which is data fidelity term. So in this case, you do a gradient descent on the G term, on the data fidelity term. Here, you take a proximal step of the data fidelity term. Okay? Well, the second term is a proximal of H, which is a prior information here, regularizer. Here also you have proximal of H. Basically, if you think of, and the third terms we don't need to describe, it's also essential for convergence properties of algorithms, but they're not structurally as important. But if you think about those algorithms, both, they alternate between two types of steps. The first step goes from less data consistent, so this is this guy, to more data consistent. Okay? So which means you try to minimize the data fidelity term. In ADMM, it's the same thing, but using the proximal instead of the gradient, it goes from less data consistent to more data consistent. And the second step, it's basically a denoising step where we go from more noisy image to less noisy image. And you basically alternate between increasing data consistency and removing noise, increasing data consistency and removing noise, until you converge. Okay? Now the key is if you actually use the mathematical proximal operators, you can prove you'll end up minimizing this thing. So you're alternating between two operators, but you're minimizing some global objective function, which makes sense. And there's some statements you can make about the rate convergence and everything, so on and so forth. But basically, that's a structure of two algorithms. And then this has been extensively used. Here's this example. There are thousands of papers on the topic. I'm not going to go through the example, but here's an example where you just have physics coming through multiple scattering and sparsity-based prior. If you combine the two, basically you can reduce amount of measurements from 81 holograms to 6 holograms, but this one doesn't use any machine learning. Okay, so just to summarize what we discussed. So this is the first part of the talk. We discussed about formulating imaging inverse problems as regularized inversion. We saw that denoising is a key component there, and traditional sparsity optimization kind of fits in there very nicely. And two very popular algorithms are FIST and ADMM. So those were extremely popular. Why? Because they allow you to naturally avoid differentiating whatever is non-smooth. So you avoid the gradients by using the proximals. Okay? Any questions so far? Good. So now let's move on to the second part, which is regularization by artifact removal, which will essentially try to bridge this topic of proximal optimization. So the question I'm going to start with, okay, is there a better way to regularize things than using sparsity in a fixed basis, right? So we saw that by using proximal operators, we can really infuse non-trivial structural priors inside the inverse problems. But can we do better than that? And if we think about whatever is happening in deep learning, the answer is probably yes, because there are incredible types of neural networks that we see that can really enforce all kinds of advanced structures to images. So this is one, I attended ICCV last year. This was from Samsung team. They take the famous images and try to synthesize different views of those images. So this is an example of Mona Lisa speaking, where you take one image from output. But the point I want to make here is this: the reason this kind of works is this kind of deep neural nets are very good at representing visual structures. They're very, very efficient in terms of representing, and they're quite flexible. You can train them in different ways and try to get a lot of benefit by using these things. Now, can we use them as priors, structural priors for images, right? And many knows that. And this is a funny example that comes up with my conversation with Charlie Bauman. Whenever you get a good result and you have a PhD student working on this, wow, this result is excellent by using neural network. Why? And his student gave this very nice quote: "This is a power of deep neural network," right? So, so this looks like a magic, but it's really the capability of people investing a lot of engineering effort to design this kind of networks that we can now use for other types of tasks. So here's a simple recipe, and this is an extremely popular paper by Michael and his team that gave this recipe first. It's a way to train neural networks. So here's one mechanism you can apply to biomedical imaging. You have a scanner, imaging system, that can give you raw data. So you can do a short scan and a long scan, for example, in MRI. So long scan could be like 5-minute scan, where you tell the person not to breathe, you do some protocol, you scan these things. But then you can do a short scan, which kind of does 1-minute scan, which of course will have much more artifacts, right? So if I do a short scan and I just do a inverse FFT, I would get something like this. We saw those artifacts. You can see the image is very poor quality. Now, if I do long scan, then I can do some form of image reconstruction, for example, sparsity-based one. And then I get something I can call a gold standard. So I put quotes there. So I get better quality image because it's a longer scan and better processing of the algorithm. Now what I'm going to do is put this neural network here. So I can put, I called it denoising neural network. And it tries to take this input image, produce an output, and we do supervised learning, try to get those two output and this gold standard as close as possible. So this recipe has been very, very successful. Okay, so it has definitely many advantages. So here's a short representation of it. We take an input image, we train artifact removal network, and we get the output image by training it on some gold standard, right? So the question we might ask is, okay, what are some key benefits of this approach, right? So we all probably can identify some key benefits. The first is it's very easy to implement and deploy. It took, when I joined my university, it took me maybe 6 months to get the first version of implementation. You don't need to do anything. You just get, some framework, you get the data, you deploy it. The second benefit is it's extremely fast at test time. So once the network is trained, it's trivial to apply. You just pass it through the neural network, you get the output. So which is very good for volumetric imaging. If you have a lot of data set, you don't want to iterate through, you just pass it through. And then finally, there is no need to explicitly model anything. Okay, you really just model things end to end. You don't worry about things, you put it all in, you hope you get something out, and it's the power of deep neural network. You get something very powerful. Okay, now the second question, what are the key limitations of this approach? Can anybody contribute? What are the key limitations of this approach?
Well, lack of robustness.
Lack of robustness, definitely.
And for example, lack of consistency.
Definitely. Those are good points. Well, it's not criticism of your work. It's just a discussion of we have to be nuanced when we discuss advantages of the algorithms or disadvantages. So those are potentially the drawbacks. Any other ideas? Yep.
So what happens when you image a different organ, or you have the patient upside down or left and right in the scanner?
Exactly, very much related also to robustness. But what happens if your geometry changes or something changes? Can we still deploy it, right? It's a very good question. Anybody else? Yeah?
It's artifact still in your golden standard between there.
Definitely. If you keep on, we saw those examples actually yesterday, a couple of scary ones. If you still have artifacts, I think in your talk, right, you showed some nice ones. If you still have, artifacts in your examples, you get them after training. Any other? Yep. Yeah, it's very related to Michael said. It's difficult to impose data consistency. And yeah, so let me just put three that I thought of, and they're very related. Okay, one, need to ground truth, which is related to what you said. There's no ground truth, essentially. We're getting some form of ground truth. And in dynamic imaging, it's very hard to get the ground truth, right? And in optical imaging, it's also a big challenge. It's very hard to get the ground truth. The second one, consistency to the data measured is not explicit. There's no explicit metric to do this, so we just train it, and the hope is that training process on the training data gives us some form of data consistency. And then finally, it does not exploit known physical models and information. Say you have a system where you have changes, but some kind of things you could easily model, but not easy to train, then you cannot easily bake it in the test time, so you cannot exploit those things very easily. So how can we go around? And this is a paper that came out, plug-and-play priors, that kind of helped me to think of this way as a connection to traditional proximal optimization. Okay, so plug-and-play priors, what I want to talk to you about, is a mechanism to partially overcome some of the limitations that we discussed, and we'll talk about it in a moment. So let's think about training neural networks only as a denoiser. Okay, so what does this mean? You have a noisy image, as we discussed, there's a denoiser. It could be a proximal operator, but we forget that. We're going to just put a neural network here, and we just train it to remove that noise. So you can do it synthetically on your computer. You load a bunch of images, you add white Gaussian noise to it, you remove. Why do we want to do it? It sounds strange. Why do you really want to do it? The reason is what we really want to use this neural network is to learn the features of the images that we want. We don't necessarily want it to learn the geometry of scanning or other things. We really want it to focus on certain features that we want to focus. So this procedure is a simple heuristic to force it to learn the features in the data set. So it's learning to separate the noise from the data. And that's kind of a simple hack to get it to learn features. Now, once we have the denoiser, now we have the operators that we discussed. We can have a d sigma, which just goes from more noisy to less noisy, less data consistent to more data consistent. This is a gradient step, or less data consistent model, which is a proximal. And we can just basically end up with those two algorithms. Those are the plug-and-play algorithms that have been initially developed by Venkatakrishnan and Charlie Bauman's team. And the algorithm is very simple. You take ADMM. This is a data consistency term, which comes from the forward model. A neural network only will come as a prior denoiser. It replaces a proximal operator. And then the third one is just related to the algorithmic step. Actually, let me put this way. Yeah. And then you can all put the same thing into the FISTA framework, where you just have a gradient descent step which enforces data consistency, a neural network that enforces consistency with a prior data set, and then you alternate between the two to converge. So this is a simple recipe that was called plug-and-play priors, right? So basically, in this framework, it's just like proximal optimization. You alternate between the data consistency and denoising. But here's a key thing. We have explicit separation between the forward model which bakes in all the physics of data acquisition, geometry of scanning, anything else you can model by hand, from the prior, which is a denoiser, which simply tries to fuse in some information from the training data set. Now, it's also explicitly decoupled, and you can control their trade-offs. You can explicitly control their trade-offs. Okay? So this is plug-and-play priors, which is quite old. It came out in 2013. The second algorithm I want to talk to you about is RED. I want to cover those two because two of them kind of think in a similar direction, but do a complementary type of work. So what's RED? It's called regularization by denoising, and it was introduced by a team of Elad, Miki Elad at Technion. So it's called regularization by denoising algorithm. It has this very simple, deceptively simple form, which just looks like a gradient descent, right? So I have an iterative algorithm. I have this thing G. If this was simply the gradient of data fidelity term, I would be minimizing maybe a likelihood function or something like this. Okay? But what they did is they added another term here, which is simply tau times, this is a constant times, difference or residual of the output and input of the neural network. Okay? X minus a denoiser X. So that was the regularization by denoising. So it looks this, and if you read the papers, there is a machinery explaining this. In fact, if it satisfies some conditions, and there are a couple of papers on that topic, then you can, in fact, write that this minimization problem will be minimizing regularized inverse problem with a regularizer given of this form. Okay? So if you do satisfy some conditions, and the conditions are locally homogeneous and symmetric Jacobian conditions on the denoisers, then you would be satisfying this condition. Okay? However, the only limitation of the RED, one key limitation of RED, actually not the only, is that this convex interpretation significantly restricts class of denoisers we can use. In fact, many neural networks will not be compatible with this regularization by denoising perspective in the following way. If you look at the appendix of that paper that has a nice title, Can We Mimic Any Denoiser? It says, in fact, that you really need the one homogeneous functions. Okay, so that will limit you denoisers to have. So it should be kind of a close to a norm type of. So total variation would not fit this thing, or Wavelet thresholding would not fit this framework. So you would not be able to represent those in this form. Okay? However, it still gives us very elegant framework to think about those problems by explicitly decoupling this term from this term. So let me give you an alternative interpretation, which we call regularization by artifact removal, which is very much related to RED, but will have two key benefits of RED, and I'll talk about this. So what we want to talk about, we want to give away the interpretation of an explicit regularizer, and we want to replace a denoiser by a more general image restoration function. Okay? So it's the same type of gradient descent. I have data fidelity, so it's a gradient of data fit, and I have a prior, which is a residual between some image restoration network and the output. Okay? So how can we interpret this? Well, let's look at the fixed points of this operator G. No, actually this should be zero set, not fixed point. Zero set of this operator G. Let's look at the zero set. So what's the zero set? It's a set of all inputs X such that this thing is zero, right? Why do we care about this set? Because in fact, this algorithm is converging to that set. The moment this G is zero, we got the fixed point of this algorithm, right? So that's really what we're trying to minimize. It's a fixed point iteration over some operator, okay? But now that operator has actually a nice interpretation. So if the zeros of the data fidelity term and fixed points of this, so what are the fixed points? Its fixed points are X such that input and output are the same. So all the vectors such that this operator acts as an identity. So what does this mean from the perspective of image restoration or image denoising network? It means it doesn't have to denoise, or it doesn't have to restore that image. It means it's a points which are clean according to this neural network. So if there exists a value which is at the intersection of those two sets, which is clean and consistent with the data, then the solution will be in that zero set. That X star will be in that zero set. Also, if the intersection is empty, if there is no element which satisfies both conditions, then basically we're really doing a trade-off between the two, explicitly controlled by tau. So when tau is zero, we're dropping the neural network. When tau has value, we're more and more pushing towards the fixed points of that neural network. Okay? So this is an interpretation of the regularization by denoising. But here we kind of give away optimization perspective. We don't have any more explicit optimization point. We're really looking at the fixed point interpretation of things. Okay? So this might look a little bit heuristic, right, initially, if you look at this kind of algorithm. But actually, there's a rich monotone operator theory, which is completely built around fixed points of different types of operators. And in fact, even proximal optimization can be analyzed in that way. So let me show you some kind of results that we summarized in these things. So first thing, if you run this algorithm, and you put 3 assumptions. So here assumptions 1 is that there exists a fixed point. The second assumption is that the forward operator, the G, is convex. And the third assumption is that the neural network is non-expansive. So what's non-expansive? It means it's Lipschitz 1. So proximal operators are non-expansive. So we're just broadening a little bit beyond those proximal operators by saying it doesn't have to be proximal. It just has to be non-expansive. So if you satisfy all 3 things from monotone operator theory, you can just see that this thing will be monotonically decreasing with the rate 1/t, which is very much similar to traditional gradient descent algorithm convergence analysis. Okay? And the second thing you can see is that it's completely backward compatible. If, in fact, you replace that image restoration by a proximal operator, you will be minimizing an objective, but not exactly. So this is T. So this is a F plus H, G plus H. So you have this distance to minimizer. It's going down as 1/t here. But there's a fixed constant here. But that constant is controlled by tau. So by taking that tau to any arbitrarily small value, you can get it as close as possible to actual minimizer. So all I want to say here, it's completely backward compatible with traditional optimization perspective. Okay? So you can do some statements about this to kind of give it a little bit more credibility to this kind of algorithms. But here's another advantage of this perspective of going beyond proximal operators and in fact going beyond the denoisers. It gives us a nice recipe to leverage this paper which came out last year called Noise to Noise. Who is here familiar with the work Noise to Noise? Few people. So Noise to Noise is a very interesting paper. I recommend everybody to read it, but let me link it to what I'm describing right now, okay? It can give us a very nice recipe to train image restoration networks without having any ground truth. And now combine it with a forward model, okay? So we'll spend some time on this plot, maybe a couple of minutes. Something I don't know is a ground truth image xi, right? So xi would be a true image that I can never see. Imagine I can actually get 2 views of that image, okay? So I can get h1i here and h2i. So I'll get 2 measurements. So those could be projections in CT or K-space measurements in MRI or anything else. It could be a blurry image in a camera, okay? So I have 2 realizations. Those are available. This I don't have access. One thing I can do is I can train a network to map this thing back to image space, okay? So I have the same CNN prior, which takes this data and maps it back to image space. Now what I do is, instead of using h1i here, I take h2i here. So I take the second guy and I put here, which means I project it to data space, but of the second measurement. Okay, so here I have h1. This is my measurement. I pass it through the neural network. I get some form of image. I want to judge the quality of that image, so I'm going to take it through the second operator and bring it here. And I'm going to take the second measurement and minimize the loss between the 2. And I do the same thing here, but I minimize the loss with respect to this operator. Okay? So what are we doing? We're actually having 2 views of the object, and we're trying to train a neural network to map the one view to another view of the object. So when does this make sense? So imagine none of those H are perfect, but there is I here, it's a data set. If I take ensemble of the whole data set, assume that I get full coverage of all the information. For example, if in K-space, each HI might be subsampled, but of union of all HI gets me complete coverage of K-space. Then this kind of training would be able to infuse all this information to each other. And this is kind of comes. Essentially, if you read the noise-to-noise paper, what you really want to have in the expectation, you want to have that you get the full coverage of the object space or the unknown image space. Okay? However, each individual measurement doesn't have to be perfect. So this is really good for MRI case. In particular, I'm going to show you an example of 3D MRI where people are breathing, we're getting radial acquisition. We never get a perfect one, But each time we get different radial patterns. So if I take ensemble of everything, it looks like a densely sampled pattern. So let me take a minute. Any questions on this? Yep.
You never use the two measurements simultaneously and one net?
So here, no, actually you can add this too. So this is a beautiful flexibility of training neural networks. You can even add another term which would say mapping this guy to itself. So you can do some form of residual-like mapping. You can add those terms. But typically this was sufficient in our case already to get you a very good image restoration network. But designing of that loss function is, there's a lot of flexibility in designing that loss function. Okay? So here's a simple recipe that would allow you to train a neural network without any underlying ground truths. But you can have a lot more flexibility. And if you look at this paper or even original papers, there is a little bit more nuanced discussion around this topic.
Just to answer, how do you construct your outputs?
Which one? This one?
No, your final output.
This one? Oh, so in this case, it's just a training. I'm training a restoration network. So I want to update those theta's, the weights of this neural network, but I don't have a ground truth to supervise. I cannot use this X. So what I'm using to supervise is two separate independent measurements to supervise my network. It's still a supervised training, but without an ideal ground truth. So each individual view of the object can be imperfect. Okay? Each individual view can be imperfect. So it might take a second for people to appreciate, and I'll be very happy to discuss this later. But it's very flexible. For now, take my word. If you're interested, I'm willing to discuss. But it's a very flexible framework to train. It's not my invention, it was this, but it perfectly combines with this iterative perspective I'm going to show you later. So let me move on now. So here's an example to show you what it would look like. So this is a problem of 4D MRI. So there's a breathing motion, it's a 3D volume. So what we do is we acquire one free breathing MRI sequence, so there's case-based measurements. Then there's a special spoke to track the motion. So we separate it to 10 motion phases. But now here what happens is it's heavily subsampled. So what happens is you're going to end up with 1 minute free breathing MRI scan, which means each individual image is heavily covered with artifacts. So this is MCNUFFT for 1 minute. What I'm calling gold standard is what would happen if I would do a 5-minute measurement and use sparsity-based reconstruction. So this result is a 5-minute acquisition with sparsity measurement data. Our goal is to go hopefully from this to something like this, or potentially even better, if we can. Okay? So this is MCNUFFT. This is region from the gold standard. This is a training where you use this as a supervision signal to map this guy to this. That's what I showed you in a simple framework where we train to map MCNUFFT to this gold standard. This is UNIT 3D. This is the output of this noise-to-noise trained restoration network. So the scheme I showed you here, if you use this scheme to train, you would end up with this. Okay? Now, if you plug this into iterative algorithm, you would end up with something like this. Okay? So here, the difference, so this uses exactly the same neural network as here, but it doesn't iterate. It doesn't reuse the data consistency with a forward model. If you additionally do 10 more iterations, you get this. So you also use the measurement operator several times. Okay? So this is basically a combination of this neural network with a forward model. So here's another example. But let me show you this. So here's how it would look like. So we run 10 iterations. Why does this framework is very nice? Is because already neural network gets you a very good initialization. You pass through this restoration network, it gets you a very good initialization. But you can still see some artifacts and now as we iterate 10 iterations, you can refine the image quite substantially by combining the information from the measurement operator, which is a case-based operator, and the prior, which is this image restoration network. Okay? So here's for the second example. You can see how amount of, so here's a comparison is with respect to fixed point. So you can see with very few iterations, you get very close to the fixed point of the algorithm because you already initialized with a very good starting point. Okay? So here's a summary of this little discussion. So what did we talk about? I talked to you about plug and play and red frameworks, but then I said, okay, let's relax this optimization perspective, and let's just assume an image restoration network. Now that flexibility allows us to reuse this noise-to-noise thing to train it for many measurement setups by having two independent views of the object. Okay? Now once you train it, by having it with an iterative algorithm, you can do substantially better. And the cost is not so much more. It's only 10 iterations that we generally use for this form of reconstruction. Because if you think about it, we start from a good condition, and there's only benefit in reusing the forward model to refine the information, to reinterpret the data. Okay? Any questions? Yeah, a quick one.
Yeah, so you are iterating, and then you had some result on some kind of convergence. Yeah. But if you take just this noise to noise, I mean, what guarantee do you have that it converges?
Oh, so noise to noise training. So if you read the noise to noise paper, if expected value of your noisy patterns equivalent to the noise-free image, so in expectation, that noise to noise should be, so long your convex optimization is the same, is minimizing the same objective function. Okay, so there are guarantees for noise to noise. So if in expectation, let me call those xij, which means xi is data set, j are views of the object, so those are noisy. If I take expectation of this, if this is equal to xi, then you're training the same thing. That's a guarantee. Okay, so it's not without merit. Okay, and now within here, now we also have a guarantee in terms of algorithmic convergence with respect to G, but that's a separate topic. Let me leave the other questions to Zen because I want to quickly cover the other topic. So the nice thing about this rare algorithm that I told, so it was a very flexible one, but I want to quickly cover the case where now our data fidelity has a lot of different types of data fidelities. In particular, I showed you optical tomography, where we get many intensity measurements. How can we reconstruct it, right? So in this case, computing the full gradient basically needs you to compute capital L gradients, where you use all the measurements. A simple hack, which we all know, this is SGD, we all use it in machine learning, is to use mini batches, which is a subset of measurements. So you have, gradient hat here with respect to B, where B is much smaller than L. And this is essentially this streaming variant of rare, which we call Simba, which is simply put here. It's very easy to understand. Instead of using a full gradient at every iteration for the data fidelity term, we use just a mini batch gradient, which is over a subset of it. So you use only B over L. So it allows you to significantly reduce the per iteration cost. Okay, instead of using all illumination, I randomly shuffle through a subset of illumination at every iteration. And then I combine it also with a image restoration network here. So if you do this, again, we can reuse the fixed point monotone operator theory. You can show it. It is really like SGD. That algorithm will converge as a 1 over square root of t rate of convergence. It's a nice, clean algorithm. It has the same interpretation. So this converges to the same set of fixed points as the original rare algorithm. So it's completely compatible when it converges. But in principle, it reduces your per iteration cost significantly in terms of memory and potentially time. So let me show you. You want to take a picture? Here. I'll put the slides up. Here's a little illustration that puts a point in. So 20/20 rare, 26 Simba, 66 rare. So what is this? So it's a tomographic setting. We have 60 intensity measurements. So 60 per 60 means use every single one at every single iteration. Okay? 20/20 means you randomly pick 20 of them, but at every iteration you use the same fixed 20. 20 out of 60 means use randomly 20 at every iteration. You do mini batches of size 20 and you cycle through. Now you have solid ones and dashed ones. Solid means you use Nestor of acceleration. Solid means it's non-accelerated, the simple one. Okay, so now let's look at it. So if we look at per iteration, so here's time. This is per iteration. So let's look at time. So if I pick the fastest one, as you can see, 2060 Simba. So it has the same per iteration cost as a 20/20 algorithm, but it gets much higher SNR because it cycles through them, which makes sense. However, it's significantly faster than 60/60 algorithm. So you can see the other one by needing to per iteration, it kind of converges slower in time. So it's much less dramatic in terms of iteration, but it's much more visible when we look in time. And of course, acceleration does significant improvement over non-acceleration, so you can see the curves here. So this is just a simple hack to illustrate this. And here's a little result on actual experimental measured data, where we use neural networks to regularize this problem versus a Tikhonov regularization here. And this was an algorithm that was published before. We can talk about this later. What I want to show is that what really this allows us to do is to process big images. So here we have 1024 by 1024 by 25 image, where we have hundreds of illuminations that we can process for reconstruction by cycling through them. And we have done even bigger ones, but those ones, I didn't put them into the slide. So, but when it converges as good as original rare algorithm. You can see the error here is like order of 0.01. So it's much less than 1% error. So that kind of summarizes my general talk today. So I talked about this rare algorithm, which is regularization by artifact removal, and I showed the second general improvement on it, which is basically a stochastic version of it, which takes subset of measurements at every iteration. I think that concludes my talk. Thank you very much.